Hello everyone, welcome to the session on Introduction to the AWS Container Services. Today we are going to explore the world of containerization and how it can help you build, deploy and manage your application on AWS. As you may know, containerization is a powerful tool that allows you to package your software code and its dependencies into a single portable unit that can run consistently across different environments. AWS offers a range of container services that can help you leverage the benefits of containerization, including ECR, ECS, EKS, and Fargate. In this session, we will take a closer look at each of these services and learn how they can help you simplify your deployment process. So, without further ado, let's get started. This is the agenda today we are going to follow. First, we are going to have a brief introduction about the AWS Container Services, and then we are going to discuss about why we need containers and a little bit about the history, what are containers, and journey to containerization, and difference between container and the image. And also then we are going to discuss about the Elastic Container Registry, ECR, and we are going to have a demo on that, create ECR repository, and build image locally and push them to the remote repository. Then we are going to have a discussion about the Elastic Container Service, and we are going to create a ECS cluster service and ECS task and deploy the container we have created. Then also we are going to discuss about the Elastic Kubernetes service, and of course a demo on that. And also lastly we are going to discuss about the best practices we can follow when you are building images and the containerization. Okay, these are the services we have today in AWS as container services. First services we have AWS Elastic Container Registry. Basically we can use it to store, manage and deploy container services. We are going to have a closer look in this session. Also we have Elastic Container Service, so that's the AWS Container Orchestration solution. And also we have AWS Managed Kubernetes Service, that's EKS, and we are going to discuss about that, and also a little bit of comparison on ECS and EKS, what are the benefits of each service. And also AWS Fargate, serverless computing option for the containers. So these are the main core services we are going to try out today. And also we have couple of other services like AWS App2 Container and AWS Copilot. So basically those two services are high level abstraction layers for the container services. For example, App2 Container is a command line tool for migrating and modernizing Java and .NET web application into container format. So it can basically analyze and build inventory of application running in bare metal or Amazon EC2 or in a cloud. So it can discover and analyze all the dependencies and extract the application and create a Docker image, and it can help you to deploy that Docker your build artifact to the AWS cloud. Also AWS Copilot is a command line interface that help you to easily build your container application. So it can get your Docker file as input and then ask a couple of questions and understand what is the pattern you want to follow. Is it a web service or web application? Then based on that it will deploy your app and kind of a high level wizard. So Yeah, and also we have Red Hat OpenShift service on AWS. It's manage OpenShift on cloud. Also we can say it's Kubernetes manage Kubernetes service with Red Hat support. Okay, why we need containers? So as you know that name coming from shipping industry, just as a shipping container is a standard portable and self-contained unit that can be loaded and shipped on a cargo ship. Software containers are also a standard portable and self-contained unit that can loaded and shipped on any infrastructure platform. So if you talk about standardization, so shipping containers are standard size and shape, which make them easy to load, transport and stack. So similarly, software containers are also built to a standard format and specification, so which make them easy to package, deploy and run on any supported infrastructure system. Also, if we talk about portability, shipping containers can loaded and shipped on a cargo ship or truck regardless of the destination. Similarly, software containers can be deployed and run on any infrastructure platform regardless of the underlying operating system or hardware. Also, if we talk about shipping container, shipping containers are designed to be self-contained, which with everything needed to be transport good from one place to another. Similarly, software containers are designed to be self-contained with everything needed to run and application, including application code, dependencies and configuration file. Shipping containers also designed to be efficient with minimal waste space and maximum cargo capacity. Similarly, software containers are designed to be efficient with minimal resource overhead and maximum application performance. So if we talk about a couple of use case scenarios, I mean when you run, let's say you have to configure one of your web service or your application on a physical server or on your laptop. So you have your infrastructure layer, and on top of that your host operating system. In there you will install all the dependencies and libraries that you need for your application. Then you can have your application on that particular server, right? So imagine so that your server have big hardware, CPU and memory and storage, and your application consuming very less amount of hardware for the moment. You may need to configure couple of other services also here. But the problem is, so probably the second application, it may dependencies and the library, it may need probably something else, and both cannot be live on the probably same operating system. It may probably different version or compatibility issues probably. I think as a software developers, everyone experience this issue in one point of view development life, right? So it's very difficult problem to handle when you need to configure multiple application in a single server. So manage all these dependencies. So journey to containerization begin with virtualization, with the process of running multiple virtual machine on a single physical server. So virtualization allow multiple operating system to run on a single physical server, which help reduce the hardware cost and improve resource utilization. As we know, virtualization works by using hypervisor, create virtual machine which are isolated from each other from underlying physical hardware. So each VM has its own operating system. Then on top of that we can have application and resources which are attached from abstracted from physical hardware. So in that case we can have multiple application on same physical server, abstracting the hardware layer using hypervisor. While virtualization provide many benefits it also has some limitation. So VMs are heavy. So in that they require their own operating system and virtualized hardware, which can take up to significant resources. They also take longer start and stop, which can slow down the deployment processes. So the containerization image as a solution to this limitation. So containerization provides a way to run multiple isolated application on single host operating system without the overhead of full virtual machine. So containers work by sharing the host operating system and kernel with other containers, which make them much lighter and faster than VMs. Each container include only the necessary libraries, dependencies, and configuration file need to run the application, making them much more efficient than VM. The journey from virtualization to containerization has been driven by the need for more efficient and flexible application deployment. While virtualization provide many benefits, it also had limitation that made it less than ideal for certain type of application. Containerization have emerged as a way to address these limitations and provide a more efficient and flexible way to run application. So it's not about VM or containers. It's about using the both technologies effectively to get most out of it. So if we talk about road to containers, in early days when multiple terminals connected to the same mainframe, so need for resources to be shared among many users connect to same mainframe. So if we didn't manage resource properly, so one bad process can cause problem to everyone and crash the main computer. So over the time, there were many features added to the Linux kernel to isolate resources and more and more. To journey to container begin with the chroot command, which was introduced in Unix version 7 in 1979. The chroot command allow process with its children to operate in a restricted environment where only a subset of the file system is visible. This can be used to create lightweight sandbox for running application. Later on, in 1990s, the FreeBSD operating system introduced a new feature called JS, which built on the chroot concept by providing additional security and isolation mechanism. JL allow multiple instances of system to run simultaneously on same physical host, each with their own view of the system, network interface, and process. In 2002, Linux introduced a new feature called namespaces, which is similar to JL but more flexible. Namespaces allow different processors to have their own isolated view of system resources, such as the file system, network interface, and process IDs. So namespace provided a way to create a lightweight virtualization without need for full-blown virtual machine. Then in 2007, the Linux introduced concept of CG groups, control groups, which allow for resource management and allocation for processes. CG groups, can limit the amount of CPU, memory, and other resources that the process can use, making it possible to run multiple containers on the same host without contention. Together chroot, JS, and namespace and CG groups provide the building blocks for containerization. And containers are, as you can see, containers are not a specific concept but rather combination of these features that have been refined over time to provide more lightweight, flexible, and efficient way of packaging the deploying application. So with that, in 2008, we had Linux LXC containers, and in 2013 we had Docker. So Docker played a significant role in making containerization more accessible and popular by abstracting away many of the complexities involved in creating and managing containers. It simplifies the process of creating and running containers. And yeah, then the most popular open source project in the internet, Kubernetes, everyone may have. So container orchestration tool, very popular. So as you can see, containers are completely isolated environment, as in they can have their own process, network interface, volume mount, just like virtual machine, except they all share the same OS kernel. We can say the Linux namespace is the main feature that enable us to create isolate instance of resources. And namespace is the box we build around the process, and control groups allow you to decide the size of the box by limiting the resources. Okay, container versus images. Image is a read-only immutable template that define how a container will be realized, and container is a runtime instance of an image. This is the example Docker file. So Docker file is a text file that contains a set of instructions for building a Docker image. So it's essentially lightweight standalone executable package that includes everything needed for run a piece of software, including app code and runtime environment, libraries, and dependencies. And Docker use layered approach to build image, where each instruction in the Docker file create a new layer in the image. Each layer is represent change to a file system and is built on top of previous layer. When a layer is added, Docker only stores the changes made to the file system rather than creating a complete copy of the entire file system. This approach allows Docker to build the image quickly and efficiently, as well as to reuse layers that have already been built. The read-only base layer is the image that container is based on, and it's contain the file and directories are part of the original image. This layer is shared between all containers that are based on the same image and never modified. So what happened when containers started? Docker create a new read-write layer on top of the read-only base layer. This read-write layer is where any changes to the file system made during runtime are stored. For example, if file is added, modified, or deleted in the container, these changes are stored in the read-write layer. The read-write layer is isolated to container, which means that any change made to the file system in one container do not affect other containers that are based on same image. Additionally, any changes made the read-write layer are discarded when the container is stopped, which means that next time container is started, it will start with a clean file system. Yeah, also, as we have already discussed, the image is a blueprint, and we can have many instances, many containers from that image. Okay, it's a demo time. We have discussed about little bit of containerization history, and we discussed about image layers and Docker image. So in here we are going to create the image and check the layers, and we are going to test it locally, and then probably we can create a remote repository. We are talking about ECR in next, and we can create ECR repo and push our image to ECR repo. All the demos we are showing today available on this repository. You can find it here in GitHub under LK Ravi, AWS Container Services. So our first demo is on building image. So all the resources and Docker file we are discussing available in this image build directory, and also the instruction to build image and run image and check layers, everything available in the readme file. So today we are going to build a nginx image. We will discuss about the content of that. Let me open the directory here. So this is the Docker file. We are using Alpine base image, and on top of that we are installing nginx, and we are adding new user, and we are creating new directory for HTML files, and we are copying the nginx configuration file, and also copy our web application. I am using sample HTML index file, and we are exposing port 80 and start the nginx process. So this is the my sample HTML file, index file, and the nginx configuration. Okay, let's build it and see how. I am going to cd into image build folder. We have nginx folder there. Also we have Docker file and HTML file and the nginx configuration. So I'm going to build the Docker image. For that I'm going to use docker build command, docker build, and we can tag image as my nginx, and you can find the Docker file in current folder. So we can insert that with dot, and let's see how it goes. Yeah, it's getting the base image from docker.io and run all our layers. It's done. Let's see our images. We can do that by typing docker images, and we have my nginx image built 10 seconds ago. It's around 11 megabyte. Let's run it and see. We have these images here. To run it locally, I can use docker run command. As you can have seen in the Docker file, we have export port 80. So I'm going to bind port 80 on my local machine to the container port like this, and then we are going to use my image name. Yeah, we have start the container in another terminal. Probably we can curl it. Yeah, we are getting our index page. Let's try it in browser as well, localhost. Yeah, we can see our web page is running. Okay, let's stop it. And we have discussed about the image layers as well, so let's check that. Docker images, and to check the layers we can use docker history command, with image id, docker history and image id, and you can see all the layers from bottom to top, getting the base layer, and adding nginx, add user, adding file and configuration file, and copy index file, and exposing port. How these layers organize, you can see. Okay, all good. and then we have created image, we have tested locally, and we have checked the layer. As per our demo, then we have to create a remote repo and push image to remote repo. Just before that, we will quickly discuss about the ECR. This is going to be our remote repository. So Amazon ECR is a fully managed container registry offering high performance hosting, so you can reliably deploy application images and artifacts anywhere. So let's see how we can use Amazon ECR for all future container deployments in ECS, EKS, and everything. First, we have to create the ECR repository. Let me show you. If we go to Amazon, console, and if we click on the Amazon Elastic Container Registry, you can go there and see what are the available registries. Currently, we have one sample repository. If we need to create a new one, we can create a new repository from here by go through this wizard, but I'm not going to follow that way. So we have several options that we can interact with in Amazon services. We can use this Amazon console, web console, to access all the services, and also we have AWS CLI that we can run all the CLI command from the terminal, and also we have SDKs that also we can use programmatically access any of the services. But I prefer using infrastructure as code tool like Terraform, so it will be easy for me to maintain all the required code. So I have created this Terraform script. So in there, basically, I have defined AWS ECR repository resources with this name ECR demo. Also, if you check in our demo repository, in there it contains all the instruction for you to create the ECR repository using Terraform, and how to log in, and also how to tag your local image to your ECR as in your ECR registry, and how to push it. So we are going to follow this instruction now. Yeah. So we are going to run this Terraform code first, so then we can have ECR registry. So these are the output values I have defined. Once it created using Terraform, I will get the repository URL and the repository ID and the ARN. So then I know what is my repository URL for future users. So I'll have new terminal, and I'm going to go ECR directory, and in there I can find all the Terraform file. To run Terraform code, as you can see in the instruction page here, you have to initialize your Terraform code, so it will help your code to download all the required providers. In this case, we are using AWS provider to access all these AWS services. So once you define any Terraform resources in your code, once you initialize, it will download all the Terraform provider to your local, And then using Terraform plan, you can see what are the resources it's going to create, and if you're happy with it, you can do the Terraform apply. Then it will help you to apply all the resources. So let's do Terraform init. So it will initialize the backend and download all the providers. Then we'll do Terraform plan. So it will show you it's going to add one resource, that's AWS ECR repository, and this is the name, and these attributes we will know after apply. Okay, then let's apply it and see. We can also do auto approve, as we already know what's going to happen. Yeah, it's done. Within few seconds it's created our repository, and also it given all the defined output. So we know our registry ID is this, and this is our repository URL. So let's have a look in the console. We'll refresh here and see whether, yeah, ECR demo, it's created, and currently we don't have any images here. So we are going to tag our image and push it here. Okay, to push image to your ECR registry, first you have to authenticate your Docker client to Amazon ECR registry. For that you can find this command from ECR documentation. So what it's going to do, it's get the ECR login password and pipe into the Docker login command. Let's try that. Yeah, it's login succeed. And also, as you can see, I'm using these environment variable for AWS account ID and region. So those variable already available in my environment. That's why it's resolving to the correct values. So you can use it like this. So you can have hard-coded values when you're trying this. Make sure that you have all the value for environment variable I am using here, basically for the AWS account ID and the region. Yeah, and now we already authenticate ourselves. Then we have Docker images. We already built our Nginx image. Now we have to tag our image with the our ECR registry repo. So I'm going to tag it like this, Docker tag my Nginx image, and this is the repo URL for my ECR repo. As I mentioned earlier, account ID, region, and the ECR repo tag, all these values are available in my environment, so it will resolve to the correct values. Yeah, it's done. Now we check the Docker images, you can see there's a new image tagged to the same image, but it's currently tagged with our ECR repository with the tag. So once we done that, we just need to do the Docker push. We can do like this, Docker push with the same repository URL. It will start pushing all the layers to our remote repository we have created few minutes back. Yeah, it's pushed, and we can check it from WCLI, ECR describe image, and repository name ECR repo, and we can see our repository, and we have image there, and we can see it from console as well. Currently it's nothing there, so we are going to just refresh the console. Yeah, and we can see our image push into the ECR repository. So that's it for this demo. So we have discussed how to create image, how to check layer, and we have tested locally, and we have created remote repository, and we authenticate our Docker client to the ECR repo, and we tag the image and push it. Now we know how to run single instance of application with a simple Docker run command. So we are going to discuss about container orchestration. So container orchestration refers to the process of managing and automating the deployment of scaling and maintenance of containerized application. So what happened when that single app instance crash, or number of users get increased and single app instance is not enough to handle the load? So that definitely we know we can have multiple container instances, right? So what happened that the underlying container host crashes? So we know that we need to have multiple container host instance to make sure the availability of the underlying application. So as you can see, there are many parameters that we need to take care when it comes to large application with hundreds or thousands of container. We have to make sure the availability of container application, underlying host, and networking. When if app instance is down, there's someone who need to take care, bring another instance of that application. It's not possible to manage all these possibilities manually. So we can build our own script which can be used to solve this problem up to some extent, but we don't need to reinvent the wheel. The container orchestration is just a solution for that. Container orchestration solution ideally consists with a set of tools and a script that we need to manage the containers in large scale. Yeah, container orchestration refers to the process of managing and automating the deployment, scaling, and maintenance of containerized application. So it enables you to automate tasks such as provisioning resources, deploying containers, scaling up and down depending on the demand, and managing the networking between containers. They also provide features for monitoring the health of the containers, managing their storage, and handling updates and upgrades. So container orchestration is important because it enables developers to focus on writing code and building application rather than worrying about all these operational issues. If we summarize the main responsibilities of orchestrator, so it's manage networking and access, track state of containers, scale services, do load balancing, and relocate in case of unresponsive host, service discovery, attribute storage to containers. So in here, this is just one example. So this is a very popular Kubernetes architecture. So as you can see, there's a control plane and in the data plane. So as you can see in the container plane, there are so many components that responsible for the each of the characteristics we have discussed in the previous slide. So as you can see, there's a API server. It's a gatekeeper for everything in Kubernetes, and there's also a distributed storage as a backend for the Kubernetes store all the clustered state. It's called etcd. And also there's many controls like kube control manager, kube scheduler, kube proxy. So each of these services, responsible for managing, for example, kube scheduler. It's handle the placement. Scheduler decide which node should run which ports. Likewise, there are well structured content orchestration tools and platforms that we can use instead of managing that our own. So I'm not going to go much detail in the Kubernetes architecture. Just want to give some brief idea. That's there's well managed solution already available. We just need to leverage it. ECS. So Amazon ECS is a fully managed container orchestration service that make it easy for us to deploy, manage, and scale containerized application in AWS. So in ECS we can create ECS cluster. It contains all required services to manage the individual containers, as we have discussed earlier. All the control processes available in ECS control plane. As this is a AWS managed service, we don't need to worry about managing the control plane. Also, we have option not to manage the data plane as well. For example, delegating the infrastructure management to AWS, we can do that using Fargate profile. Fargate is serverless computing option for the containers. So if we talk about a little bit about the Fargate advantages, so in there, so no need to worry about provisioning and managing servers. So it's pay only for what we use, and on demand, easy to scale up and set up, and also fully manage, as we only need to worry about our apps. Also, if we have if we need more control and flexibility over the underlying infrastructure, we can also have EC2 as option as well. So then you will have more control and flexibility over your infrastructure, but you have to manage it. So if we look at the components of the ECS, task definition is the blueprint, and describe how to run a containerized application on ECS. So it includes the information such as Docker image to use, amount of CPU and memory needed, and any container link. So port mapping, like we define in Docker container. So this task definition version and can be update, modify configuration of a container. So all the definition as a blueprint available in this task definition. So from the task definition, we can create an instance that is called task. So running the container details with it. So multiple tasks can be created from one task definition. So it's like a Docker file and the containers. Yeah. So with all these tasks, we have service. A service is a logical grouping of tasks that are running the same task definition. So it ensures that the specific number of tasks are running and automatically restart fail if tasks fail. So we can say in service, okay, I need to have for instance of tasks from this particular service. Likewise, that's a logical grouping. So all these services run on AWS container instance. So container instance is a EC2 instance that running the ECS agent with communicate with ECS service and run Docker containers. So this agent is a daemon that run on each EC2 instance, or Fargate task, and it's responsible for registering the instance with ECS service, and it's monitoring and reporting the status of task and starting stopping container. Yeah, with all it, it's build a ECS cluster. So cluster is a group of ECS container instances Amazon, ECS handle the logic of scheduling, maintaining, and handling scaling requests for these instances. It's also take away the work of finding the optimal placement for each task on your CPU and memory needs. Yeah, similarly, you can have multiple cluster defined in ECS. For example, if you have development, pre-production, and production environment, you can have multiple clusters and configure your pipeline to promote your workload. So overall, ECS provide a comprehensive set of components and features for running and multiple containerized application on AWS. And all the problems we have discussed, managing all the container instances, underlying infrastructure, and the scheduling, health checks, and everything. You don't need to worry about it. And ECS going to do the heavy work for you. So this is one of the solution you can use in AWS to orchestrate your containers. Okay, for the ECS demo, we are going to explore the folder of ECS, and we have this ECRTF. In here also we are going to use Terraform for creating ECS cluster and task definition and service. Let me quickly walk you through the script. So in here I've defined AWS ECS cluster resource, and in here you can see the ECS task definition. As we have discussed earlier, that's where we have defined all the CPU, memory, and the image and the container definition we are going to use. So as you can see, we are using the same image we have built previously, and we have push it to the ECR Elastic Container Registry, and we are using that particular image here. So that's our task. And also we have create AWS ECS service as a Fargate as a launch type. Then we don't need to manage infrastructure here. Yeah, that's about it. So we are going to create this resource and see how application work in ECS cluster. Before that, let me show you the ECS clusters in the AWS console. Yeah, as you can see, currently we don't have any clusters, so we are going to create it and go back to the services and cd into ECS folder. There we have our Terraform script. So as we have discussed earlier, we are going to do Terraform init first, and it's going to download all the required provider and plugins. So it's done. Then we can do Terraform plan and see what are the resources it's going to create for us. Yeah, it's going to create 7 resources. We can see all the ECS security group, policy attachment, and the task definition, and the cluster and the service, all the resources. I'm going to apply it, Terraform apply. I'm going to auto approve it. So just wanted to remind you, all these scripts are available on GitHub repository lkravi/AWS Container Services. You can find all these scripts and you can try it yourself. If you have any questions or clarification required, you can reach out to me on Twitter and LinkedIn. I'm available on Twitter with at LKRavi handle. Yes, it's created all the resources, 7 resources added. Let's refresh. Okay, yeah, it's already created, and you can see it's just starting the task. One task is pending, so it will take a few seconds to create the task. If you create the cluster, click the cluster, you can see our service, deployment and task. One task completed. If you go to task, we can see, okay, yeah, our task is running. Let's go to task, and in there we can find out public IP for our task. And as we can see, in the task we have our nginx image we have created in our first demo. So let's see, we can access the task. Yes, it's up and running. As we can see now, we have hosted our container we have built previously on Elastic Container Service. So the definition for this task, as you can see, available in here. So we define what is the image and CPU memory, and in the service we have defined decide count as 1. So that's why we have only one task from it. Let's say if we need multiple tasks from it, so we can increase this desired count, and then it will create a couple of tasks from whatever you define number. It will create tasks from it. Yeah, so that's pretty much it for the ECS demo. Amazon Elastic Kubernetes Service. Amazon EKS is a managed Kubernetes service to run Kubernetes in the AWS cloud and on on-premises data centers as well. So it's a Kubernetes as a service. In the cloud, Amazon EKS automatically manages the availability and scalability of the Kubernetes control plane nodes, responsible for scheduling containers, managing application availability, storage, cluster data, and other key tasks. So as we have shown before in the Kubernetes architecture, all the control plane components managed by AWS. So you can even offload the data plane workloads using AWS Fargate as well as a serverless computing option. Otherwise, you can have ECS node groups or ECS as the data plane for running all the workloads in the EKS cluster. So main benefit using Kubernetes as a managed Kubernetes in AWS in EKS. So it's integrated with other AWS services as well. For example, IAM for user and permission, CloudWatch for monitoring, and Elastic Load Balancer for load balancing, VPC for networking. So you can gel with all the other core AWS services and utilize well the Kubernetes service in AWS platform. So if we take EKS and ECS, both manage the control plane, and even though ECS control plane is free, we can discuss couple of advantages and disadvantages here. So in EKS, so its availability of generic Kubernetes API is a huge advantages, because as Kubernetes is open source with a large community and well established tool set, so you can leverage the generic Kubernetes API for many things. and with that it's easy to migrate to another platform as well. So most of these managed Kubernetes flavors available almost all the cloud, like GKE on Google, and Azure Kubernetes service, and Elastic Kubernetes service in AWS, or even in on-premises you can install Kubernetes cluster by your own. So similarly, in each case, the Kubernetes API is similar, so it's easy to migrate from one to another. So that's one advantage. But you have to be mindful about when you are integrating with other core AWS services. If you depend too much on all the other AWS services, it will be a bit difficult for you to migrate to another platform. Otherwise, same all Kubernetes objects and the API, so it will be very easy to migrate. In the other hand, ECS APIs are generic to AWS. It's not open source API sets as Kubernetes. So all the control plane and everything managed by AWS, and also the AWS specific API. So if you are all these concept code, task definition, task services, and ECS cluster, all these things are specific to AWS. So migration is difficult compared to EKS, but the only benefit is control plane is free. But if you compare, if you are having large organization with very large set of microservices, and you need to host multiple services, compared to ECS, EKS would be better option, as you may have a lot of options there in the open source world. You don't need to for most of the common problems, there's always already resolved solution available, and with large community support. For EKS demo, that's all the instruction available in our GitHub repository. You can see. For that also, I'm using Terraform to initialize EKS cluster. In here I'm using EKS blueprint, that also open source project initiated by AWS. So using blueprints we can easily instantiate EKS cluster with all the required add-on and components, and the security teams and everything configured very easily. It's kind of a template, and we just need to tick whatever the components that we need for the EKS cluster. It help us to provision EKS cluster easily, without having all those things configured by ourselves. How easy for us use that kind of a template. Otherwise, first you have to provision EKS cluster, then you have to install all that on one by one. Then you have to make sure all the security and the access configured for the cluster, and we can use here GitHub tool like Argo for the deployment. So if you use this kind of a template, you can in one go, I'll go through the code and explain to you. You can easily configure everything within a couple of minutes, and also you can spin up EKS environment with all the required component within 10 to 15 minutes. So that's a huge advantage. So you don't want to spend a lot of time on managing all this infrastructure. So it's already done for you. All the instruction available here, how to access the cluster, and some of the components, like how to access the Argo CD UI. Argo CD is the GitHub tool we are using for the CD part. CD means continuous delivery part. So we are using Argo CD to sync up all the application that we are going to deploy to this cluster, and also for the observability, I just will show you. We have configured a couple of Prometheus Grafana instances in this cluster. Yeah, let's go through the code. And also for all these example, we just need a network, AWVCP, VPC with required subnets and internet gateway and everything. That one, before this recording, I have already configured using this AWS VPC Terraform module. All the source code available in this network folder. If you are interested, you can have a look on that as well. I'm not going to explain all these details because this is all about containers. So this is the EKS code base. I'm going to explain main components in there. So this is the EKS blueprint module. This is the open source repository I have mentioned. So we have refer that, and we just need to define the cluster information. So from the network and subnets, as I mentioned, I have already created it, and I'm referring existing VPC ID and private subnet. Then in here I can simply define okay, manage node group for my cluster. I need m5 large. Okay, what is the minimum maximum size of the nodes? And also I can define Fargate profile. In there specifically we can define particular namespaces for that profile as well. For example, I am deploying application on team specific namespaces. That namespace start with team dash blue, team dash red, or something like that. So I can define if namespace start with team dash, all these workload go to this Fargate profile. So in that case, I don't need to manage infrastructure for that workload in that namespaces. If that those teams deploying any applications, so infrastructure management for that particular namespace will be take care of using Fargate. And also if we need to have our own node groups, we can do that as well. So for example, I'm just adding here EKS node group and Fargate profile as well. And also I have mentioned we can in this template we can define teams as well. So in here we can define platform team and application team. For example, we can define multiple app teams as well. In here one team blue dev I have defined, and you can also restrict the quota as well, how many CPU memory and the port services they can deploy into this cluster. As you can see, you can easily manage. Let's say if it is a small company and you need to have a dev environment to test all microservices, and you are having multiple team, you can easily spin up EKS cluster with the required compute option, node groups or Fargate, and define all your teams. And based on their requirement, you can define the quota as well, limit. Okay, how many app teams and what is the quota, and who are the users. If you have AWS IAM users, you can associate those users here. In this example, only me itself only, so I am using my current AWS user as admin, and I'm adding same user for the app team as well. But if you need, you can configure multiple teams with different users. As you can see, it's pretty much easy to use. So that's the cluster part. And this is the most interesting part, Kubernetes add-on. As you can see, in the Kubernetes cluster you have to have with all these add-ons for essential for EKS cluster, like VPC CNI, Core DNS, proxy, all those things. You just need to enable the flag, and it will make sure it will install in your cluster. Apart from that, I mentioned that I'm using Argo CD as a GitHub tool for our deployments. So I can simply enable the Argo CD, and it will make sure our Terraform script will make sure it will install Argo CD into our cluster. And here I can define, where, Argo CD can find our, workloads. For example, we are deploying our sample, contain image we have created in our previous demos, right? So I have added the, pod spec and all this information here. Deployment file, you can see we are using same image we have built earlier and push it to the ECR. I have created deployment and service here, and also in this case I have added ingress object as well. I'll show you. I provision a load balancer, and we can access this workload from this URL as well. So yeah, this is how it's configured here. And yeah, this is the ingress part I mentioned. So I enable AWS load balancer, and enable the ingress as well. Ingress means in the Kubernetes context it's kind of a reverse proxy that you can have load balancer, and coming all the traffic through load balancer to your ingress controller. And you can define ingress object like for example, in this case, if you come with this host, you can redirect all those traffic to this particular service in Kubernetes service on port 80. Yeah, similarly you can have once you have ingress controller installed, you can have as many as ingress object you want. And similarly, as you can see how easy to install all these components, your favorite add-ons like Prometheus, Grafana and cloud matrices. It's just a matter of enabling those features. If you go to this EKS blueprints add-on repository, you can see how many all the available add-ons. Almost all the favorite open source tools are available there. You can if you need to simply use it, just define it here. That's it. Yeah, let's create this cluster similarly using Terraform and see how it works. We are in our AWS Container Service folder. Let's cd into EKS folder, and we can find out all the Terraform file. As usual, we just do Terraform init to initialize all the providers. In this case we are using AWS provider, and Helm and kubectl, a lot of providers. So all these providers need to initialize first. It's done. Then we can do Terraform plan and see. It will take couple of minutes. Yeah, as you can see, it's going to create a lot of resources, 97 resources to be added. All the EKS cluster, node groups, and the Kubernetes add-ons, all the components we have defined, they are in the scripts. Okay, let's apply it and see. Okay, our cluster creation is completed now. You can see the Terraform output. All the resources created now. And the cluster endpoint, cluster ID, and all the detail we need for the cluster is available here. Yeah, all the instruction to connect to the cluster available in our GitHub repository. For example, to connect the cluster, we need to update our kubectl config. So we can update like this. You can get the configuration. Yeah, then we can try to kubectl get pods. Let's try. We can get connect to the cluster. Yeah, we can see all the workloads, CloudWatch, Argo CD, and Grafana, all the things we have defined in the blueprint, the Prometheus, and also the demo application we have mentioned about. Let's check about kubectl. Yeah, we can see 2 Fargate nodes and 3 node group we have defined in the profile. And we can check all the services as well. And we can see that ingress controller we have talking about previously. It's deploy as a load balancer service, and also AWS load balancer, network load balancer also deployed and configured here. So then if we configure this load balancer URL from redirect our traffic from route 53 to this load balancer, as we have defined our ingress URL app.eks.this URL, we should be able to access our application. So yeah, before that we can try we can try to A86 is this update our route 53. I'm going to edit this record, and A86 this is my new load balancer. I'm going to update it. It's done. And also we can see the EKS cluster here in console now, as we have created it. We can see container on EKS cluster, and we can see all the information regarding that and all the add-ons we have installed. Similarly, we discuss about the GitOps previously, so we can access the Argo CD URL, and for that in our Terraform code we have created custom secret, and we use that secret for Argo CD configuration. So we can get that secret from here, from AWS Secret Manager, and then we can use kubectl port forwarding to access the Argo CD. I'm binding Argo CD server on port 8080 like this. So then we should be able to access Argo CD on port 8080. localhost 8080. Yeah, we may need to log in, so we already got the password here. All these instruction available in GitHub repo, so you can follow that along if you are confusing that where I'm getting all these things. Yeah, this is the Argo CD UI, and you can see all the Argo CD manage add-ons here. Also the application, the workload dev, we have defined our application in team blue dev. We can see how it's configured here, all the Kubernetes objects. This is a deployment we have defined, and the endpoint service and the pods. We have 2 pods deployed. Yeah, we can try to access this endpoint and see whether our application is working now. Yeah, so as we can see, we have deployed our application to Kubernetes cluster as well, and also we have exposed our application through load balancer, and we have also map DNS as well using Route 53. I have this domain registered for me, and I'm using this wildcard domain for my Kubernetes cluster. So as you can see, using couple of line of code, we can achieve whole lot of things. We can configure whole Kubernetes cluster with all the add-ons, and even the continuous delivery part. We don't need to manually deploy any application. All the application we just need to define as Argo CD app of apps like this, and we just need to define where we are storing our application configuration. Then it will automatically get these deployments and all the Kubernetes manifest file, and it will sync up with the cluster. If you need to deploy any other application, you just need to add all the YAML file into your workload folder you have defined in your EKS configuration file here, workloads. So then it will eventually sync up with your cluster. Currently we are accessing Argo CD using port forwarding. If you check here, you can see all the how to access the from ECS and how to access the Grafana and deploying sample dashboard. All the information available here. Even yeah, that's pretty much of it. You can try out this Terraform script available in GitHub repo and see it yourself. So now we have completed building container image in our local, and we have tested it out locally, and then we have pushed it into the ECR, elastic container repository. Then we have used the same image and deployed to the ECS service, and we create a task definition and create a service and deploy into the ECS cluster. And then finally we have used that same image we have built to deploy the same application into the EKS cluster as well. So this is the EKS cluster we have created. One last thing, so all these resources if you are no longer need, because it will be charged for you for all the resources you are using in the AWS. So if you are done with your testing, you just need to destroy all these components you have created For example, let's destroy this ECS, terraform destroy, you can destroy your ECS, all the components we have created previously. Similarly, all the instructions available for the EKS cluster as well in the GitHub repository. You can follow along and make sure you have remove all the resources you have created. Otherwise, there will be costing in your AWS account. It will take couple of minutes to complete the deletion. Yep, it's completed. Next, we are going to discuss about the best practices on building images. So in microservices world, so we are discussing about in microservices, we are thinking about split our application into small services that can be reused, remixed, and shared. So enabling small, nimble, decoupled teams and processors. Better tooling enable encourage microservices. So when you're thinking about that, having small images always help us. So basically it will help us to quickly pull those images, and since it's smaller, that means it available only the required packages and the source code in that image, so less attacker surface. And when we are having only the essentials in the image, so that means less frequent updates. We don't need to update all the components. Apart from that, so when it come to building images, it's always better that you can make your base image your own. Why I'm saying that? So ideally, so when we are doing production releases, normally we are getting our base image from Docker hub, or probably some public repository. So if you can have it more closer to our build environment, probably in our ECR image, and do security scanning, and if there's anything we need to harden the image, and mostly make it available more closer to the build environment always help. So we control the availability of our base image, and we know all the things on it. And yeah, most important thing, also using explicit tags, mostly when it comes to production for testing and this kind of a demo, it's okay, you go with latest image. But when it comes to production, you should ideally it should be more specific, and you should be aware of what is the version you are using, instead of having latest tag. Then whoever tag whatever the version as a latest, you will getting. So there should be there are breaking changes. So ideally it's always better to use explicit tag instead of go with latest. Multi-stage build, so this is a very useful thing. You can save a lot of size and time in your build process. For example, this is one of the example, this Prometheus image. So when it come to build as a same single Docker file, it's taking 2.38 gigabyte. But if when it break into multi-stage build, so you can take away a lot of size, and it's around 150 megabytes now, so huge save on the capacity side. Then it will make sure that image will pull quicker, and only available whatever you need in the image. uh, if I quickly show you this example, uh, in here, this Prometheus build, so downloading all the required dependencies, and building in a single Docker file like this. This is the one example we have show you. So it's taking around 25 minutes with 2.38 GB in size. But if you break apart into multiple stages, so in base builder, you just download all the required components and build it, and then in the final image, you only copy whatever the final build artifact into your final, and you configure that's there. So then all the intermediate step, downloading these packages, and extracting, building, all these intermediate steps you don't want in your final image. So by splitting into multi-stage, and get whatever only you need for your final, you can as you can see, you can save a lot of space and time in here. With the multi-stage in your final image, it's just only 150 megabyte. So even for the optimization, you can use parallel multi-stage. So this download step you can have in parallel, so it will not probably not save the size, but time wise you can gain more, and you can reduce some more time. Yeah, that's one thing. Also, yeah, this is a very common thing, reduce layers by combining related operations. So as we can see now, initial slides, so each and every instruction reflect as a new layer in Docker. So if we can combine the related operation, so all these instruction go into single layer, that will helps. Also leverage the build cache. This is to optimize your build process and save time there. This is really important, as you know that build cache help to make subsequent build faster. Once cache is warmed with layers, and when build is referring same unmodified layer, which means you didn't do any changes to that particular layer, so build process use same cache layer, no need to build it again. So cache layer will invalidate if the instruction on new build include the change. For example, this if you in the main go file, if you change anything there, so then cache layer invalidate on that, and all the layers on top of that will also get invalidate as well. So what you can do to optimize, so in here if you switch the layers, and you want to do the things that change a lot toward the end of your Docker file, so that will help you. For example, compared to this source code, this change package update, installing the packages less frequent to change, right? So we are always including the same package set for this image, but you are most probably almost every build you are changing the source code, right? So in that case, if you switch these two layers, so we can utilize more cache layers, so that's help when you're building the image. Yeah, also understanding the endpoint and CMD, it's important. So CMD can be overridden from CLI. So entry point take arguments from the CLI. So according to your use case, if you don't have use case to override, if you have specific requirement for your Docker image, and what is the process it's starting, so better to use entry point. Otherwise, if you know what you're doing, you can use a CMD. Keep in mind that it can override from CLI as well. Also, use secrets instead of build dark for sensitive value. It's not recommended to pass secret to container with build dark, because those are embedded. And if you also add sensitive information as a file, and then later if you remove it, it doesn't matter, it will burn into image. So don't do that. Use secrets, and will use it will use a special mount, and not leave behind any trace of your secret also for the runtime. Yeah, that's pretty much about it. So thank you for seeing or up to this point. That means you have learned, hope you have gained something out of it. We discussed about building history of the containerization, and how it came through all the time, and discuss about the container and images, and the couple of AWS services like ECR, ECS, EKS, and Fargate. How we can easily utilize and use those services for our application deployments. I'm available on Twitter and LinkedIn. If you have any question or clarification or correction, please reach out to me. I'm happy to help anytime. Thank you very much for your time.